should disappear. Yeah. Right, so the effect of extratropical dynamics on intraseasonal propagating modes in the tropics, and this is work that I've done mainly with Séverin Thibault with a little bit of help from Stephanie Leroux. So a bit of background to start with. There's been a steady stream of literature over the years attesting to some sort of coherence between mid-latitude dynamics and convection in the tropics, and the mechanisms that have been put forward, the idea that, for example, you have an extratropical Rossby wave which can, under certain circumstances, approach the tropics and promote convergence, which will lead to convection. Or there's the other school of thought, there's the kind of global mode school of thought where the whole tropics, extratropic system is, has modes which grow on those timescales. And the attempts to model this influence has mainly taken the form of regional models which have been run in the tropics, where you do interesting things with the boundary conditions and you try to establish the effect of those boundary conditions on the tropical variance. The main person who's done that work recently is Pallav Ray, and he's shown with the regional models that getting the variance right on the boundaries is one of the essential ingredients to having a decent simulation of the MJO in the tropics, and he's shown that the boundary conditions with the extratropics are at least as important as the upstream conditions within the tropics. So our contribution is to continue with that kind of approach, start doing some longer runs, so we're not looking at case studies, we're trying to establish if there's any generic or systematic behavior. So we'll start by introducing a few concepts here. This is very seasonal. What do you think, it's like a TV game show, okay? Which of these pictures best represents the influence of the extratropics on the tropics? On the top left there we have what you might call a forced response. On the top right, there have been some volunteers in the streets of San Francisco. Recently, the Salvation Army are out there demonstrating that with this system, it doesn't matter what you do, those bells will still make the same infernal noise. And then the little girl on the left there is a bit more picky. You've got to push her at the right frequency, otherwise she won't achieve high amplitude. Jimmy, on the other hand, does not need any encouragement at all. He just stands in front of his amp, gets some feedback going, and he can just sustain that note. It'll just ring on its own. So which of these four? How do we design modeling experiments to distinguish between these possibilities? Well, when you want to do a regional model in a tropical band, you have certain methodological problems. So imagine those gray bars are the boundaries between the tropics and the extratropics. In reality, you have influence in both directions. As tropical modelers, we tend to think of the system like this, that the extratropics will provide the boundary conditions and then the tropical flow will react to those boundary conditions. That leads us to do these kinds of experiments where the blue arrow now represents our model simulation of the red arrow subject to the green boundary conditions which have come, we think, from the mid-latitudes. But the problem with that could be, what if what we're actually doing is this? Because there's no reason to suppose that the values of the variables on those boundaries are uniquely influenced by the extratropics. The actual realization in the tropics might also influence those values. So how do we establish the best protocol? Where do we put those boundaries? And we've done some simple experiments to start with. I'm going to show you some results from a global dynamical model. So this model has no convection. It has no moisture variable. It's just a dry primitive equation model, and it has no business simulating an MJO, okay? So diagnostics from a free run of that model, it's been forced empirically, so it gives a decent simulation of the global circulation. And yeah, we'll look at these Wheeler-Collardis diagrams, and on the left you have the reanalysis, so you can see Rossby waves, you can see, how can I point at? Yeah, you can see Kelvin waves there, Rossby waves, and there's the MJO, right? Now there's my model, it has Kelvin waves, but unsurprisingly no MJO. So what happens now if I constrain the extratropics with data? So I replace the model solution with data outside 30 degrees north and south, and then look at the free solution in the tropics. Well, still no MJO. So far, so good. So let's see what happens now when we move those boundaries closer to the equator. Okay? Are we going to get some influence? Well, what have we here? At the risk of sounding like a teenage girl, oh my God, that should just like totally not be there. I mean, what would happen if we were to try that with a model, a proper model that does have convection, like WRF? Well, that's the next thing we're going to do, okay? Because, so we'll take that cautionary tale and we'll put the boundaries at 30 north and 30 south. And we'll design some experiments to see what the, try and distinguish between the boundary-induced variance in the tropical band and the free variance that is intrinsic to the tropics. So we have 3 experiments that we're going to do. One is called the reference experiment, where the boundaries conclude, well, it's just NCEP data on the boundaries, okay? The notch experiment, where we have excluded intraseasonal timescales from the boundaries, and the climatological experiment, where the boundaries contain nothing but a repeated annual cycle. There's a diurnal cycle as well. Okay, so no intraseasonal variability, no synoptic variability, and no interannual variability. And we'll go further than that. We'll also, for each of these runs, we'll do each run twice. So we'll have the same run with the same boundary conditions, but we'll just change the initial condition to throw some noise into the system, and then we can diagnose the difference between these twin runs to try and tell what's the variance internal to the system, which is independent of the boundary conditions. So how do we do with the model? The reference run is on the left there, the observations on the right. The blue shading is the rainfall, which is reasonably well situated in the model. It's a bit heavy. The contours are the low-level zonal wind, a little bit strong in the Indian Ocean, but reasonably well situated again. If you look at the notch experiment, so there we've deprived the model of its intraseasonal variance on the boundaries, and the climatology looks remarkably similar, so that has not suffered from that operation. On the other hand, if you look at the climatology run on the right, we've now deprived the boundaries of the synoptic scales, and the climatology has degraded considerably. Okay? So what about the variance? So we have the reference run top left again. This is the variance of the low-level wind. The colors show the intraseasonal band, and the variance is well situated compared to the observations on the right, a little bit strong. If you look now at the notch experiment below, it's clearly the variance is weaker. So from this we infer that the intraseasonal variability on the boundaries is having some influence on the variance. The climatology is not so well situated, probably because the basic state's not very good, and also the variance is weaker. How about the boundary forced versus intrinsic variability in each run? We already have an idea of that from these experiments, but now let's look at the twin runs. And so there are the 2 reference runs, and not surprisingly, they look pretty much exactly the same. Okay? If you look on the lower right now, there's the variance of the difference between those 2 runs. And look at that equation on the top right. That variance should have a maximum value of twice the variance in one of the reference runs if those reference runs are independent from one another. Obviously, they're not. They're not independent because they have the same boundary conditions. So the variance of the difference is rather weaker, but it's still of the same order of magnitude, which shows that the intrinsic variability is also important, but the boundary-induced variability is important as well, okay? Now, what if we look at the notch run for the same setup? Then the variance has obviously got weaker. The variance of the difference has actually got stronger. So not only is it actually approaching that limit of twice the variance in one of the runs. So that shows us what we expected, that the internal variance is more important now. And it's even showing us that if you remove a certain amount of variance from the boundaries, then the internal variance might compensate. Now, I think that's an interesting result, because that tells you that even if you think that in a tropics-only run you can explain the variance, that doesn't necessarily mean that that's actually what's happening. The extratropics actually replaces that variance with a with boundary-induced variance. Okay, so that's the magnitude. How about propagation? So let's look at some one-point correlation map, or one-region correlation maps. This is keyed onto OLR over the maritime continent. And so we are, look, each of these boxes is a little map of the tropics. And there's our kind of correlation point. And the colors are OLR correlated onto that point, and the contours are the wind correlated onto the OLR. And that's from minus 25 days to plus 25 days, so time lag going downwards. And you can see in the observations the MJO passing through there. You can also see in the reference run, it's not quite so strong. It's not so well convectively coupled as it should be. This just shows the convectively coupled part of the solution, of course. But you can see propagating precursors in the reference run, not so much in the notch run. So we're missing something there. And the climatology run just looks like noise, like filtered noise. Same thing well, now we're looking at the two reference runs, okay, and the difference between them. Same story, really. They look very similar to one another, but in the difference field, it seems like there's less happening upstream in terms of propagating precursors. And in the notch runs, the two notch runs, again, you're not seeing very much. So I'll just wrap up with a graphic conclusion slide. The forced response idea, well, I don't think anyone ever really believed that. That's a bit of a straw man, okay? I think Jimmy has to go as well. There's obviously some importance for the extratropics here. Whether or not it's the frequency of the forcing is important, I think jury's still out, but I'm tending more towards the girl on the swing. And that's it. What kind of what? What kind of time scale? Well, yeah, we did look at some spectra. The reference run has a decent amount of variance in the MGO region. It also has a lot more variance than it should have at longer time scales. So that's something we're looking into, and we don't quite understand yet. But yeah, the spectrum if you look at the spatiotemporal spectrum on those MJO length scales, we're hitting about the right amount of power in the MJO band, but it's very skewed towards longer time scales. Yeah.